Alright, hello, welcome back to chemistry. In this video we're going to do some examples of Lewis structures. So we just figured out how to do a Lewis structure. Lewis structures have dots. You put the symbol in the middle. You put the outside electrons around the outside of the symbol, the four sides. Let's do some examples. Let's do some examples that you did Bohr structures for. So you could choose like a particularly annoying Bohr structure that you did the other day, or you could just randomly select one. Let's randomly select that one. Okay, boron, just fine. Oh, that was randomly selected. By the way, I was not like boron. Okay, let's do boron. Okay. So we are doing boron. We're going to put the symbol in the middle. So let me zoom back in and find boron's symbol. Boron's symbol is a B, just a single B. So put the symbol in the middle. I'm even going to add this to the same page because why not? Let's just do some examples. Boron has a symbol of a B. Boron has all sorts of interesting properties as an actual element. There are folks who tried to make reusable fuel out of boron, but it blows up. I would not drive a car powered by boron for that reason. But for now, we want the Lewis structure of boron. So we're going to find our Bohr, and we're going to just zone in on that outside shell. And because we know those inner shells are filled and stable, that's why we don't really, like, it's really hard to mess with an inside shell because it's protected by the outside. Yeah, just count the electrons on that outside shell. Boron has 3 electrons on its outside shell. We can also do it right here from this giant table of things. And boron's over here. Just like yesterday, we'll start from the left and count across. And we're just counting columns. We don't even care about rows really as much. Columns 1, 2, 3. There you go. It matches. Boron has 3 valence electrons on the outside shell. Boron's in the 3rd column over on the periodic table. There's a reason that we spend an entire quarter trying to figure out how to read that 1-page document, because there's just so much inside of it. Boron has 3 electrons on its outside shell, and here I just did it without like articulating it, but I distributed those 3 electrons around the outside of this symbol. So I kind of, in your mind, you've got like those 4 sides, and you can draw the 4 boxes if you would like to. You don't have to, but you're kind of imagining 4 sides to that symbol, and you're gonna evenly distribute the electrons into those sides. So in this case, we put 1 electron in each side until we ran out. Boron is in the 3rd column, so we're going to put 3 outside electrons total. But if we were to choose something with even more electrons, let's randomly choose. Oh, I might even choose something big just to show you how it works. Actually, I'll do something in the first 20 for now. Let's do oxygen. Okay. So oxygen. Put the symbol in the middle. Oxygen's symbol is O. And you're going to think about those 4 sides again. Again, you can draw them or not, and either way is correct. Eventually, you'll get to a point where you're kind of drawing the symbols, the Lewis structures, without the boxes. But for now, totally go for the boxes if that is like, if you're visually seeing is, you know, how you do. For now, let's figure out how many outside electrons oxygen has. Oxygen's over here. And we'll do it just like yesterday. We're going to start from the left and count across. We're counting columns. So 1, 2, 3, 4, 5, 6. And it works. Oxygen has 6 outside electrons. Oxygen's here. Start from the left. 1, 2, 3, 4, 5, 6. Good, good. Okay. Great. So there's our oxygen. There's our 4 sides. 6 is bigger than 4. We're going to have to do some distributing here. But don't worry. We got this. We're going to put 1 in this box, 1 in this box. 1, 2, 3, 4, 5, 6. Alright, now we've got 6 outside electrons, and they're distributed between those 4 boxes. You cannot have a half an electron, so don't worry about that. It looks off kilter, right? Like it looks like you've got 2 on 2 sides. And you do. Your paper is 2-dimensional. Your oxygen atom is 3-dimensional. We'll go deep on that someday. That's not today. This is more balanced than it appears because we had to squash it onto a flat paper. But there you go. There's your 6 valence electrons distributed into your 4 sides. We'll go deep on why there's 4 sides some other time also. Let's do a really big atom to show you another thing, which is, let's write this down. If you have a really big atom, skip the entire block of transition metals in the middle. Do I want to do that? Yes, I do. Yes, I was debating not even mentioning it. This will help preview something in week 3, which is that the transition metals are different, which is great. Differences is awesome. We'll figure out why difference is like so important and why you recognize so many metals in that transition metal block. Their difference is actually really important, like stuff like function of things, but let's not go there right now. So if you have a really big atom, skip the transition metals. Don't worry, we're going to figure out what those are. Transition metals. Okay. If you have a really big atom, skip the transition metals in the middle. Let's do it. The transition metals are... so everything that we did with the first 20 elements, we said skip the middle because there's nothing printed there. Now we're just going to say skip the middle, just skip the middle. So if you have something really big, let's just go real big because we can and why not. Let's draw a Lewis structure for... I'm thinking let's just do it. Let's just do a... This is the most intimidating Bohr structure. There's 118 protons. We're going to do a Lewis structure for oganesson. This hasn't even really been made in a lab. It's so big it like can't even like be. But we're going to draw a Lewis structure for it anyways. Really big atom. You'd be drawing 7 circles with tons of electrons if you were doing this as a Bohr. But we're gonna, among other things, we're gonna see what it means to skip the transition metals in the middle. And to visually see this, all the stuff that we skipped up here, because there was nothing printed up there, transition metals are everything that live under that. So if you would like, you can do this in color if you want. You don't have to. I'm just going to put a box around this whole thing. This whole thing here is transition metals. And again, even as you're coloring it in, you might recognize, like, oh, like, I know some of these metals. There's iron, there's copper, there's zinc. These are, like, incredibly important as, for example, building materials. They don't blow up. Yes! Transition metals are super helpful. There's gold. And you might even already kind of put together, like, there's this big basket of things. Here's a clue. They're super stable. I mean, relatively super stable compared to lots of other things. And when we look at the outside shell, we're just going to skip the whole thing. And in like 3 or 4 weeks, you're going to know exactly why. But don't worry, you're in the right spot. You have no clue at this moment. That's awesome. Coming soon, you will be able to confidently articulate exactly why. But for now, we're going to skip them. They're transition metals. They have something different going on than the other elements do. And if we're going to do organocin, because that just seems interesting, you will hopefully never draw that as a boar, unless you want to. But let's draw it as Lewis. Do it the same way that you've done every other Lewis structure. Start from the left and count across till you run into the element you're looking for. It's a big one, so we're going to skip the transition metals. Off we go. 1, 2, skip the transition metals. 3, 4, 5, 6, 7, 8. That doesn't seem so bad all of a sudden. Once we skip the transition metals, I should probably articulate this for folks who are like, hey, wait a second, what about the lanthanides and actinides? You skipped those too. Yes, also skip the lanthanides and the actinides. The lanthanides and the actinides are even weirder than the transition metals. And they actually get pretty funky. Yeah, but that is another future video. You're right, we did skip the lanthanides and actinides, as well as all the transition metals. When we're looking at the outside shell, we can skip those inside things. Ooh, that's a hint. Yeah, outside shell. Skip the transitions and the inner transitions. 1, 2, 3, 4, 5, 6, 7, 8. Your Lewis structure for organocin looks something like this. I'm making sure I'm spelling it correctly. Organocin. OG. There's a chance that you have a different symbol, like a UU something, because it wasn't named until more recently. It's so big. It's got a symbol of OG. We're going to think about those 4 sides here also. We're going to take those 8 outside electrons, because we skipped the transition metals and the inner transition metals, and we're going to go 8 valence electrons around the outside. 1, 2, 3, 4. So each box gets 1, and then we'll go back and double up. 1, 2, 3, 4, 5, 6, 7, 8. There's your Lewis structure for organocin. Even though the boar would be very difficult to draw, the Lewis, we just drew 2 Lewis structures right there. One with the boxes, one without the boxes. Both are totally fine. There's only 8 in the outer shell. Look at that. I think you're getting getting the idea. I'm thinking I'll do one more example of a like normal size thing just for fun. Let's do phosphorus. Phosphorus is here. Start from the left, count across, just like you're used to. There's phosphorus. And we'll start from the left. 1, 2. Skip the transition metals. 3, 4, 5. 5 valence electrons. You can start on any side. You can do these in any order as long as you distribute evenly to those 4 boxes before doubling up. 1, 2, 3, 4, 5. That is a Lewis structure for phosphorus. I would just go and do all of them, but I want you to have some practice that you can do entirely on your own.